Form exponential, trigonometric, and hyperbolic functions to power series. We also evaluated definite integrals that are not solvable in Calculus 2. Today, we will use power series to solve ordinary differential equations. So here are the steps in solving differential equations using power series method. First, we assume a solution in the form of a power series with unknown coefficients. So let y be equal to the summation of a sub m x to the m from m equals 0 to infinity. Second, find the derivatives of y. So y prime is equal to the summation of m a sub m x to the m minus 1 from m equals 1 to infinity. We note that we simply use the derivative of x to the m, wherein the derivative of x to the m is m x to the m minus 1, and we simply copy the constant a sub m. Then we can take the second derivative. The second derivative is the summation of m times m minus 1 times a sub m x to the m minus 2 from m equals to infinity. For this particular expression, we get the derivative of x to the m minus 1, which is m minus 1 times x to the m minus 2, and we copy the coefficients m times a sub n. We also note that after differentiation, you have to start with m equals 1 for the first derivative, and you have to start with m equals 2 for the second derivative. Fourth, substitute the power series and the series obtained by differentiation to the given differential equation. And finally, find a power series that will satisfy the differential equation. We note that the number of power series depends on the order of the differential equation. For first order differential equations, we only need to look for a single power series. But for second order differential equation, we need to find two power series. So let us have an example, and this example that can be validated by at 55. So solve the differential equation given by y prime minus 3y equals 0 using power series method. Since the differential equation is a first order differential equation, we only need to substitute the power series and its first derivative. So first step, assume that the solution is the power series. Second step, get the first derivative. That is y prime equals the summation of n times a sub n x to the n minus 1 from n equals 1 to infinity. And substitute y and y prime to the differential equation. So you will end up with y prime minus 3y equals 0 implies that the summation of n times a sub n x to the n minus 1 from n equals 1 to infinity minus 3 times the summation of a sub n x to the n from n equals 0 to infinity must be equivalent to 0. Let us simplify. We transpose the second power series to the right side. But then by inspection, we will see that the exponents of the powers of the two power series are not equal. For the left member, the exponent is n minus 1, and for the right member, the exponent is n. So to obtain equal powers of x, we need to adjust the summation indices by replacing n by n plus 1 in the left-hand sum to obtain the given expression. So we will end up with summation of n plus 1 times a sub n plus 1 times x raised to n from n equals 0 to infinity. We note that the left expression was transformed, okay, by simply changing n to n plus 1. But of course, since we change n to n plus 1, the initial value of n must be changed from n equals 1 to n equals 0. So ending up with two expressions wherein we have the same powers. Now, since the left and the right member of the equation are now of the same powers, we can now solve for the recursive formula. So to find the recursive formula, we simply get the coefficient of the left member and the right member, ending up with n plus 1 times a sub n plus 1 equals 3 times a sub n. We solve for the expression with higher subscript. That is, we are going to solve for a sub n plus 1. So ending up with a sub n plus 1 equals 3 times a sub n over n plus 1. So this is the recursive formula for our solution. From the recursive formula, we can find the coefficients of the power series. So we substitute n equals 0, 1, 2, and so on to the recursive formula. The recursive formula is a sub n plus 1 equals 3 times a sub n over n plus 1. So if n is equal to 0, you will end up with a sub 1 equals 3 times a sub 0 over 1, or 3 times a sub 0. Now if n is equal to 1, you will have a sub 2 equals 3 times a sub 1 over 2. Using the expression for a sub 1, you will have 3 times a sub 0 over 2, or 3 squared times a sub 0 over 2 factorial. And if n is equal to 2, a sub 3 is equivalent to 3 times a sub 2 over 3, which is equal to 3 cubed times a sub 0 over 3 factorial. So we can see a pattern. So we can generalize the expression for a sub n. And a sub n is equal to 3 to the n times a sub 0 over n factorial. Finally, we substitute the coefficients to the assumed power series solution. Our assumed power solution is the basic power series given by y equals the summation of a sub n x to the n from n equals 0 to infinity. In addition form, a sub 0 plus a sub 1x plus a sub 2x squared, and so on. So let us substitute the values that we get from the substitution of n equals 0, n equals 1, n equals 2 to the assumed solution, and you will end up with y equals a sub 0 plus 3 times a sub 0 x plus 3 squared a sub 0 over 2 factorial x squared plus 3 cubed a sub 0 over 3 factorial x cubed, and so on. We then factor out a sub 0. So y is now equal to a sub 0 times 1 plus 3x plus 3 squared x squared over 2 factorial plus 3 cubed x cubed over 3 factorial, and so on. We now use algebra. 3 squared x squared can be written as quantity 3x squared, and 3 cubed x cubed can be written as 3x raised to 3. So, we can say that the solution to the given first order differential equation is y equals a sub 0 times the summation of 3x raised to n over n factorial from n equals 0 to infinity. Alternatively, we can present our solution using sigma notation instead of addition notation. So the assumed solution is y equals summation of a sub n x to the n from n equals 0 to infinity. We were able to find a sub n earlier, and that is 3 to the n times a sub 0 over n factorial. Using algebra, we can have the solution as y equals a sub 0 times the summation of 3x raised to n over n factorial from n equals 0 to infinity. And finally, relating our solution to our previous discussion, we can say from Taylor series that this expression is equivalent to the exponential function given by y equals a sub 0 times e raised to 3x. Let us have another example. This time, let us consider a second order differential equation. So solve the differential equation given by y double prime plus 4y equals 0 using power series method. So for our solution, since the d is a second order differential equation, we need to substitute the power series and its second derivative. So we start again with the assumed solution and then get the first derivative and then the second derivative. So substitute y and y double prime to the differential equation. Y double prime plus 4y equals 0 is now equivalent to the summation of n times n minus 1 times a sub n x to the n minus 2 from n equals 2 to infinity plus 4 times the summation of a sub n x to the n from n equals 0 to infinity equals 0. Now, rewriting the expression, transforming the second power series to the right side, we will end up with this result. And again, by inspection, we know that the powers of the left and the right members are not equal. The left member has an exponent n minus 2, while the right member has an exponent which is n. So we need to adjust the expression. And to obtain equal powers of x, we need to adjust the summation indices by replacing n by n plus 2 in the left-hand sum to obtain the given expression. So n was transformed to n plus 2, n minus 1 was transformed to n plus 1, a sub n was transformed to a sub n plus 2, and x to the n minus 2 was transformed to x raised to n. And of course, don't forget to change the initial value of n. Instead of using n equals 2, we need to use n equals 0, ending up with the left and the right member of the same powers. Since we already have expression of the same powers, we can now find the recursive formula, and that is simply equating the coefficients of the left and the right numbers. So we will end up with n plus 2 times n plus 1 times a sub n plus 2 equals negative 4 times a sub n. Solving for a sub n plus 2, we will end up with negative 4 times a sub n over n plus 2 times n plus 1. Then find the coefficients of the power series. Substitute n equals 0, 1, 2, and so on to the recursive formula. So a sub n plus 2 equals negative 4 a sub n over n plus 2 times n plus 1. We start with n equals 0. If n equals 0, then you will end up with a sub 2 equals negative 4 a sub 0 over 2 times 1, or simply negative 4 times a sub 0 over 2 factorial. Then let us solve for a sub 4. You have a sub 4 equals negative 4 times a sub 2 over 4 times 3. Using the result of a sub 2, we will end up with quantity negative 4 squared times a sub 0 over 4 factorial. We continue with even expression. A sub 6 equals negative 4 times a sub 4 over 6 times 5. Rewriting, you will have negative 4 raised to 3 times a sub 0 over 6 factorial. By inspection, you end up with even subscript, you end up with even factorial expressions. So, we now conclude that a sub 2n is equal to negative 4 raised to n times a sub 0 over 2n factorial. Now, let us go to the add expression. So, a sub 3 is equal to negative 4 a sub 1 over 3 times 2, or negative 4 times a sub 1 over 3 factorial. A sub 5 is negative 4 times a sub 3 over 5 times 4. Rewriting, you will have negative 4 squared times a sub 1 over 5 factorial. And a sub 7 will give us negative 4 times a sub 5 over 7 times 6. In factorial expression, negative 4 raised to 3 times a sub 1 over 7 factorial. We now conclude that the subscript add expressions and the right side is equivalent to an expression multiplied to a sub 1. So as a conclusion, we will have a sub 2n plus 1 equals negative 4 raised to n times a sub 1 over 2n plus 1 factorial. Finally, substitute the coefficients to the assumed power series solution. So the assumed power solution is the basic power series. Let us substitute the coefficients. So y equals a sub 0 plus a sub 1x times negative 4a sub 0 over 2 factorial times x squared plus negative 4 times a sub 1 over 3 factorial times x cubed and so on. By inspection, we can factor out a sub 0 with respect to the first, the third, and the fifth expression. And we can factor out a sub 1 with respect to the second, to the fourth, and to the sixth expression. Rewriting y using algebra, we will end up with y equals a sub 0 times 1 minus 2x squared over 2 factorial plus 2x to the fourth over 4 factorial and so on plus 1 half times a sub 1 times 2x minus 2x cubed over 3 factorial plus 2x to the fifth over 5 factorial and so on. So just like in Math 55, the differential equation is composed of two solutions because the differential equation is a second order differential equation. We also know that the expression for a sub 0 has even powers, while for the expression multiplied to a sub 1, you have odd powers. We can also express our solution in sigma notation. That is, y equals a sub 0 times the even powers plus 1 half a sub 1 times the odd powers can be written in this manner. That is y equals a sub 0 times the summation of negative 1 to the n times 2x raised to 2n over 2n factorial from n equals 0 to infinity plus 1 half times a sub 1 times the summation of negative 1 to the n times 2x raised to 2n plus 1 over 2n plus 1 factorial from n equals 0 to infinity. We note that the expression negative 1 raised to n shows that the series is an alternating series. And from our previous discussion with respect to Taylor series, you can say that a sub 0 must be multiplied by a cosine function, that is cosine 2x, meaning the even powers is actually equivalent to cosine 2x using the idea of Taylor series, while the odd expression is equivalent to sine 2x. Let us have an example of a differential equation with variable coefficient. This is the highlight of the prelim coverage. So let us solve the differential equation given by y double prime plus xy prime plus y equals 0 using power series. So we know that the coefficient of y prime is the variable x. So since the differential equation is second order, we need to substitute the power series and its derivative. So first step, the assumed solution. Second step, find the first derivative and the second derivative. Third step, substitute y prime, and y double prime to the differential equation. So y double prime plus xy prime plus y equals 0 is now equivalent to the summation of n times n minus 1 times a sub n x to the n minus 2 from n equals 2 to infinity plus the summation of n times a sub n x to the n from n equals 0 to infinity plus the summation of a sub n x to the n from n equals 0 to infinity. Okay, rewriting the expression, so we end up with a left member and a right member. Again, we know that the powers are not equivalent. So, we need to adjust by replacing n by n plus 2. And we will end up with this expression. That is summation of n plus 2 times n plus 1 times a sub n plus 2 times x to the n from n equals 0 to infinity is equal to the negative of the summation of n plus 1 times a sub n x to the n from n equals 0 to infinity. So let's find the recursive formula. So from the power series, we get the coefficients, and you will end up with n plus 2 times n plus 1 times a sub n plus 2 equals the negative n plus 1 times a sub n. Solve for a sub n plus 2, and you will get negative a sub n over n plus 2. We then find the coefficients. So substitute n equals 0, 1, 2, and so on to the recursive formula. If n equals 0, then a sub 2 is negative a sub 0 over 2. If n is equal to 2, then a sub 4 is negative a sub 2 over 4, or a sub 0 over 2 times 4. If n is 4, you will have a sub 6 equals negative a sub 4 over 6, or negative a sub 0 over 2 times 4 times 6. That can be generalized as a sub 2n equals negative 1 to the n times a sub 0 over 2 times 4 times 6, and so on until you have 2n. For the other expression, if n equals 1, you will have a sub 3 equals negative a sub 1 over 3. If n equals 3, a sub 5 is negative a sub 3 over 5, or a sub 1 over 3 times 5. And for n equals 5, a sub 7 equals negative a sub 5 over 7, or negative a sub 1 over 3 times 5 times 7. Generalized to a sub 2n plus 1 equals the negative 1 raised to n times a sub 1 over the product of 3, 5, 7, and so on until 2n plus 1. So finally, let us substitute the coefficient to the assumed power series solution, and you will end up with y equals a sub 0 plus a sub 1x plus negative a sub 0 over 2x squared plus negative a sub 1 over 3x cubed, and so on. Again, we factor a sub 0 and a sub 1, and you will end up with y equals a sub 0 times 1 minus x squared over 2 plus x to the fourth over 2 times 4, and so on, plus a sub 1 times x minus x cubed over 3 minus x to the fifth over 3 times 5. Rewriting the expression, okay, you will end up with the sigma notation. That is, y equals a sub 0 times the summation from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2 to the n times n factorial, plus a sub 1 times the summation of negative 1 to the n, x to the 2n plus 1 over 3 times 5 times 7 up to 2n plus 1 from n equals 0 to infinity. So, again, we conclude that for a second order differential equation, you will end up with an even powered terms for the coefficient of a sub 0 and an odd powered terms for the coefficient of a sub 1. So that's all for the discussion of power series solution to differential equation. Next time, we are going to discuss a special differential equation called Legendre differential equation. So this is Redentor Disles. Have a good day.